Welcome to part 2 of this playlist about the preparation of aryl amines. This video is about the uncatalyzed nucleophilic amination of aryl halides, sulfonates and related compounds. Acid and base catalysis will be included, but not catalysis by transition metals, which is discussed in part 3. The three main strategies of nucleophilic amination of aromatic electrophiles are uncatalyzed substitution, palladium or nickel catalyzed substitution, and substitutions catalyzed by copper. Uncatalyzed substitutions work best with electron-deficient arenes, such as nitrobenzenes or pyridines. Less activated arenes can, however, also undergo substitution, sometimes by intermediate formation of arynes. Regioselectivity can be an issue, though. Then, uncatalyzed substitutions often require elevated temperatures and a high concentration of reactants. Main advantages of this strategy are its simplicity, low cost, and the absence of metallic impurities or ligands in the final product. Palladium and nickel catalyzed substitutions often proceed under milder conditions than uncatalyzed substitutions, but require the optimization of a large number of parameters. The ligands are often expensive and purification of the final product can be difficult. Copper catalyzed substitutions, like uncatalyzed aminations, often require a high reaction temperature and concentration. Aromatic nucleophilic aminations of electron-deficient aryl halides usually proceed as sketched here. In a slow and rate-determining step, the amine first adds to the arene. In a second, fast step, the first intermediate is dehydrohalogenated to the final product. Thus, such reactions proceed best with the electron-withdrawing group ortho or para to the leaving group. The rate of aromatic substitutions strongly depends on the leaving group. Particularly good leaving groups are fluoride, nitride and sulfonates. Iodide and sulfinates, on the other hand, are only displaced slowly. Like bimolecular aliphatic substitutions, also aromatic substitutions can be slowed down by steric effects. Nitro groups, for instance, can only stabilize a negative charge if the three atoms are in the same plane as the arene. Orthosubstituents will push nitro groups out of plane and thus strongly decelerate substitution reactions, as in the second and fourth dinitroarene shown here. The methyl group in the third example slowed down the addition of nucleophiles by direct steric repulsion. Also, the nucleophilicity of the amine can have an impact on the rate of aromatic nucleophilic substitutions, but less so than the structure of the arene. Excluding some extreme cases, like terzbutylamine, the rate of substitution only decreases by 100-fold when going from the highly nucleophilic pyrrolidine to aniline. Solvent effects in aprotic solvents are similarly weak. As do most organic reactions, also aromatic substitutions proceed faster when the polarity of the solvent increases. In protic solvents, nucleophilic substitutions proceed as slowly as in nonpolar aprotic solvents, also because hydrogen bonding decreases the nucleophilicity of amines. Thus, such reactions are best conducted at high concentration with a minimal amount of some polar aprotic solvent, such as acetonitrile or dimethylacetamide. Also, DMF and DMSO are often used, but these are too reactive at high temperature or in the presence of strong bases and can readily decompose and cause explosions or the formation of byproducts. Sometimes the choice of solvent can influence the regioselectivity of aromatic substitutions. In this example, the regioselectivity could be changed completely by increasing the polarity of the solvent. In toluene, only isomer A was formed. In HMPA, isomer B was the main product. The likely reason for this effect was that orthosubstitution involved the concerted formation of a neutral enol, favored by apolar solvents. The para position was sterically more accessible, but addition here led to an ionic intermediate. Polar solvents lowered the energy of this intermediate and thus enhanced the rate of para substitution. Let's check some specific examples of uncatalyzed nucleophilic aminations. Electron-deficient arenes with two leaving groups can sometimes be aminated sequentially by two different amines. Here, as in the previous example, orthosubstitution occurred first. It was then possible to displace the second fluoride in refluxing dimethylacetamide, again in high yield. One problem of these fluoride displacements is that fluoride can be corrosive both to metallic and glass-lined reactors. This problem can sometimes be alleviated by precipitating fluoride as calcium fluoride. Also, benzonitriles can undergo uncatalyzed aromatic substitutions under relatively mild conditions. Here, such a reaction was complete in 6 hours at only 65 degrees Celsius. If a given aryl halide is too unreactive, one possibility to enhance the substitution rate is by reaction with a metallated amine. In this example, a substituted morpholine was lithiated and then added to lithium trifluorobenzoate. Despite the repulsive negative charge of the lithium carboxylate, the substitution proceeded cleanly at -78 degrees Celsius. Here, an aniline was metallated with sodium terz amylate and then arylated with 2-fluoronitrobenzene. The target diarylamine was obtained in excellent yield. Also, amides can be deprotonated and arylated at nitrogen with aryl halides. Unfortunately, deprotonated amides are ambident nucleophiles that often react at oxygen instead of nitrogen. In this example, though, a high yield of anilide was obtained. Addition of nucleophiles to the electron-deficient alkene apparently was reversible and did not cause any problems. This is another example of regioselective amination by aromatic substitution. The arene was not particularly electron deficient, and substitution required a high concentration, high temperature, and a long reaction time. Nevertheless, mainly one of the two possible regioisomeric products was obtained. Surprisingly, with the aid of a ruthenium complex, it was possible to reverse this regioselectivity, but a high reaction temperature was still required. Aryl fluorides are not well suited for transition metal catalyzed aromatic substitutions because few metals insert efficiently into the strong carbon-fluorine bond. Electron-deficient aryl chlorides can also be used to arylate amines. Here, despite the amino group in the aryl chloride, the amination was complete within 12 hours at 110 degrees Celsius, and surprisingly, no diaryl amines were formed. In this example, the starting arene was a substituted benzaldehyde, and still a high yield of product was obtained without any extensive Cannizzaro disproportionation. Even non-activated aryl chlorides can undergo high-yielding aminations, as shown here. However, such reactions proceed by intermediate formation of an aryne and can therefore yield two isomers. As shown here, 3 and 2-chloroanisole yield the same product upon treatment with diethylamine and potassium terzbutoxide. Strong bases in high reaction temperatures are particularly conducive to aryne formation. In the next video of this playlist, there is an example of copper-catalyzed amination of 2-chloroanisole, where only the expected 2-aminoanisole was obtained. Another way to activate amines is by borylation, as in this example. Butyllithium was required to deprotonate the initially formed borane amine adduct. Reaction of the aminoborane with 2-chlorobenzonitrile led both to the substitution of chloride and to a complete reduction of the cyano group. Pyridines are similarly electron deficient as nitrobenzenes. Here, a 4-chloropyridine reacted cleanly with an excess of a substituted piperidine without any additional base. The substitution required a high concentration of reactants and proceeded smoothly at 95 degrees Celsius. Intramolecular reactions yielding 3, 5 or 6-membered rings usually proceed faster than similar intermolecular reactions. In this example, an indoline was prepared by intramolecular aromatic substitution of bromide. The arene wasn't activated by an electron-withdrawing group, and the reaction probably proceeded by intermediate aryne formation. Nitrite is a better leaving group than iodide in aromatic nucleophilic substitutions. Here, a nitro group could be selectively displaced by dibutylamine without any extensive substitution of iodide. Even aromatic methoxy groups can sometimes be displaced by amines. In this example, an aniline was arylated by methoxybenzophenone with a catalytic amount of phosphacene base. Also 2 or 4 methoxypyridines can act as electrophilic arylating reagents. Here, lithiated diethylamine was the nucleophile. The substitution proceeded in high yield and was complete in only 10 minutes. Nucleophilic attack at the arene was faster than attack at the methyl group, and no demethylation occurred. Let's now check some potential side reactions. As already mentioned, if an arene has more than one leaving group of similar reactivity, mixtures of isomers can result. Because of the high temperatures and concentrations often required, other functional groups may react as well. Here, for instance, a Terz butyl ester was saponified by elimination of isobutene and then underwent decarboxylation. Nitroarenes are electron withdrawing, and nitrophenyl acetic acids therefore readily decarboxylate, like beta-keto acids or malonic acids. Another potential side reaction is oxidative amination. Nucleophiles add faster to hydrogen-substituted positions than to halogenated positions of electron-deficient arenes. If oxidants are present in the reaction mixture, hydride may become a good leaving group. In this example, lithiated toluidine added to an unsubstituted position of 2-chloro-4-nitropyridine, and no displacement of chloride but mostly displacement of hydride occurred. I discussed this kind of amination more thoroughly in part 5 of this video playlist. Such byproducts may even result in the absence of oxygen, because nitro groups or electron-deficient arenes can also act as hydride acceptors. Here, the main product was formed by intramolecular abstraction of hydride by a nitro group. Some electron-deficient arenes, for instance polyhalogenated benzenes, can form well-stabilized aryl anions. Such arenes may react with nucleophiles not as electrophilic arylating reagent, but as electrophilic halogenating reagent, similar to NBS. In this example, pentafluoroiodobenzene lost its iodine atom completely during amination with morpholine. Because only one equivalent of morpholine was used, I assume that DMSO was the reducing agent in this case. Here are some further examples which you can also find in the description of this video. In the next presentation of this playlist, we'll have a look at transition metal catalyzed nucleophilic aminations of haloarenes. These reactions have been investigated very thoroughly in recent decades, but as demonstrated by the examples I've just shown you, are not always a better choice than uncatalyzed substitutions. Anyway, transition metal catalysis broadens the scope of viable aromatic substitutions, and you can find plenty of examples in the next video.